First of all, I would like to say thank you for the organizers, in special Professor Elcio Orlande, Marcelo Colaco, and Antonio Leitao. My talk here is about parameter identification for forecasting models using partial differential equations. And I try to convince you that you need to take in account the time scale that you are interested in order to do your forecasting. In meteorology, for example, the meteorologists try to identify some time scale for prediction. Nowcasting means a few hours ahead. And forecasting could be 1 day up to 15 days ahead. And then when they talk about climate prediction, they are talking about 1 month or more. And so if you are in the winter time or you are in spring, and so you try to do some climate prediction for the next season, and so this is called seasonal climate prediction. And so when you are dealing with different time scale for prediction, and so you need to take into account that probably your calibration, when the calibration is expression that they use to the process to identify the parameters inside of this system of partial differential equations. Okay, I am from National Institute for Space Research, and I am from the division. Actually, my laboratory is Associate Laboratory for Computing and Applied Mathematics. Okay, I have some Amarizio Araújo. He is a professor from Federal University of Viçosa here in Brazil. And Professor Lu Minhao, he is a professor from the Nagaoka University of Technology in Japan. Okay, this is my outline of my presentation. I try to talk about some mathematical models, looking at operational forecasting, and then I'm going to talk about one representation between the surface model, between the surface and the atmosphere. How can the atmosphere and surface can change the informations? And then the idea is try to describe some procedure to identify parameters inside of this model using Mori methods. And I try to describe some objective functions and try to justify why I'm going to use more than one objective function. And finally, how can I solve this? Well, we're going to solving, this is one methods based on in genetic algorithm for multi-objective problem. And finally, some numerical results and my conclusion regards. Okay, so for example, when you are trying to do some numerical weather prediction, you need to solve this set of equations, partial differential equations. This is a particular approach for Navier-Stokes equation. And so we have a momentum equation. Oops. Here, yes. This is Navier-Stokes equation associated to continuity equation and a conservation of energy equations, and also this the gas law, ideal gas law. And so it's considered a very expensive from computational point of view problem, and you need to solve these equations for all the planets in the troposphere. But this is not only that you need to do. The job here includes to consider different processes that happen with the fluid flow dynamics. And then this one of the different processes are going to be considered. For example, radiation, cloud formation, precipitation, turbulence, soil representation, and surface model. And so for this different process, you need to have some different parameterizations in order to represent or to have a good representation of this process inside of our forecasting model. And so, for example, in terms of radiation, you need to take into account the cloud formation. And so you have the sun, absorption, reflection, scattering by the atmosphere. And so short wave radiation is coming from to the surface, and the surface we emit some radiation, but in the not short wave, but long wave radiation. And of course, this radiation emitted from the Earth, there is some absorption or reflection, scattering by the clouds, and so on. And so, and another complication is when you have a different covering over land here, water, snow, vegetation, mountains. This is a very complicated problem, because all of this different covering has different information, or all of this, the ratio of this flux between gases and radiation in the atmosphere and in the surface is going to be different. Okay, and so supposing that we are trying to identify this, the temperature in this column here, one way to address this problem is to consider the atmosphere with different layers, and each layer has a different temperature. And the radiation here is depending on the Planck function. And the Planck function, there is a relation between temperature and the radiation emit for different layers here. And so the satellite can capture all of this radiation from different temperatures emitted from the different layers in the atmosphere. And so you can compute the radiation, and so you can have some connection between radiation and the temperature. And so in principle, you can identify the temperature profile of the atmosphere. Okay. Well, we deal with this problem using, when you talked about direct problem, we have some causes, material properties, boundary conditions, initial conditions, if you have source or sink inside of your equation. And then when you have a method to solve this, and so this, we call this as a direct problem. And direct problem allow us to compute the effects. However, when you're measuring the effects and you try to identify some causes, this is called an inverse problem. And our inversion procedure could be artificial neural network. But we try also solve this problem using some presentations that you have listened here today using a regularization inverse solution. Like, for example, Tikhonov regularization, maximum entropy. Here we are looking at Tikhonov regularization of first order and maximum entropy of second order. But also, you can use a different method, for example, neural network. And in particular, we are interested the profile in the troposphere, because this is most important for numerical weather prediction. And our best result that we have computed coming from neural network. Okay. And so, this is one example of this kind of complexity that we are facing on when we are dealing this forecasting models. But in particular neural network, you can use, for example, you can implement it not only by software, but hardware. And so you can put this inside of satellite. And the satellite could be computed, the profile from the radiation that satellite is measuring. And then this is actually I'm talking about that you can solve our inverse problem by hardware device. FPGA is field programmable gate array. All right. So in some sense, you can for this particular problem, you can use a kind of smart sensor on board of satellite. If you're interested, we have some paper about it. But also turbulence. It's a very relevant process in the atmosphere. And unfortunately, or fortunately, I don't know, we have different dynamics of the turbulence when you have during the at the day and at night. And so we have the convective boundary layer, residual boundary layer, stable or nocturnal boundary layer, and we have some transitions boundary layers. And this is all of this different thermodynamics. It's going to imply in a different conditions for the planetary boundary layer. And also, well, you can think that we can identify some added diffusivities inside of these problems. And also, I can apply inverse methodology in order to compute these coefficients. However, this added diffusivity here, it's a little bit different that we are, in general, that we have dealing, for example, with diffusion. Diffusion could be characterized for a material property. But here, in turbulence, this added diffusivity, it is not a material property, but it's a property from the flow. And so if you have different flows, you are going to have different added diffusivities. And so this added diffusivity is also depending on time. Not only space, but also on time. Okay, and so you can use some inverse methodology. For example, this is, we try to identify some added diffusivity. One of measurements that you have already get from observation from the atmosphere. And this is published in Il Nuovo Movimento T. It's a journal from Italian Physics Society. And, but go back to the interaction between surface and the atmosphere. We have a lot of process here and different land covering, water, ice, and everything. And so in order to do a good representation for this, this is called a surface model, and I'm going to talk about a little bit IBIS model. Okay, this model was developed by the Center for Sustainability and the Global Environmental, SAGE. IBIS connect Earth's surface and hydrological process, terrestrial biogeochemical cycles, and dynamics of vegetation. Also, IBIS simulates the dynamics of vegetation, include Earth's surface interaction between land surface and the atmosphere, carbon and nitrogen cycles, and cycles for nutrients. IBIS is also able to simulate effects of the changes in the terrestrial carbon balance climates and atmospheric CO2 concentration. And so, here we have the atmosphere, and we have some canopy physics representing the highest level for the vegetation, and also some of the soil physics and plant physiology. And this is a canopy nitrogen allocation. And we have we call it land surface model. And then the the temperature from photosynthesis. It's important for a different process here. And this is connected with the vegetation dynamic model and below ground carbon and nitrogen cycling model. And well, all of this different process here, this takes minutes up to hours, days or weeks, and 1 year and more. And so, for example, when you have no rain, and so the plant goes to be like a sad plant. I mean, it's closed at the stomach. And when the rain starts, and so the plant looks like very happy, and so it's because they open the stomatus to drain to catch the water, and so all of this process should be considered and to model in these complex models in order to have a good representation for evapotranspiration between surface and the atmosphere. Okay, but all of this process means a lot of parameters in order to be identified. Okay, and so, for example, a list of parameters, I'm not going to do one exhaust list of these parameters. It's more than, it's a dozen parameters. And so, for example, the leaf reflectance in the upper canopy, in the visible range, and the same thing, but considering a near infrared band. Other parameter is leaf transmittance in the upper canopy, in the visible band. The same property, but considering the near infrared band. Sheet guiding factor in the upper canopy. Okay, this could be take a -1, 0, or 1 is horizontal, and so on. Well, a lot of parameters. Okay, and then, for example, this is I start here with 1, 2, 5, and I jump just to have more than 40 parameters to represent inside of this scheme. And then, but yes, we have a lot of parameters, but we need to identify the relevance of these parameters. According to the Pareto's law, few parameters represent much more information, or there is much more relevance for the model than other ones. And so the minority part of the parameters have more relevance than the majority part of these parameters. And well, and so you need to identify this sensitivity analysis in order to identify the clusters of parameters related to the importance or relevance of these parameters to our model. Okay, and so in terms of sensitivity analysis, there are 3 strategies to do this analysis. One is screening in order to identify the most relevant parameters. Local sensitivity, it's computed by derivatives. This is the impact of the parameter related to the model. And global sensitivity, this is associated uncertainty quantification. And the Morris method, it's a global screening method where this method tries to detect negligible effects, linear and additive effects, and nonlinear or coupling parameter effects. And in order to identify this nonlinear or coupling parameter effects, and also try to other 2 features here, you are going to characterize all parameters using 2 metrics. One is average, and another one is a variance. And I'm going to show you how you can do this. Well, and so Morris method, the assumption, the first assumption is that parameters belong to a set with a finite cardinality, and sensitivity measurements is going to be an average or mean and variance. And we are going to, instead of to use standard average, we are going to consider this mu square representing the absolute value for this variable here, x. Okay, and so this matrix represents the average effect on the model output, and the variance is the second order parameter effect. This is representing the non-linearity associated to the parameters or coupling between different parameters, and are going to compute this using R trajectories for m-dimensional. This dimension here is related to space of parameters. And so for computing the sensitivity, sensitivity is called elementary effect. 2 points are necessary, at least 2 points, in order to compute the derivative. Okay? And so, so this could be 2 RM evaluations. But Morris proposed a scheme to perform only R plus 1 multiplied by M evaluations. This is a reduction of evaluations, and in particular, this is important if you have a very complex and if your model, it's a very intensive from computational point of view. So, for example, this is for example, this parameter here, WK, and so this is our derivative in order to identify the sensitivity associated to this parameter, WK, but you are going to have several evaluations, several realizations for this in order to have a kind of statistics. You need data in order to compute the statistic, average and variance. And this is going to, according to this method, we start from here and go to another in order to compute these 2 values here. And for this, I'm going to compute for another one and another one. And so for this is a 2-dimensional and 3-dimensional. And if you have a higher dimension problem, and you can use this in an appropriate way. Okay. But for this problem here, we are interested that you have a model that could be a very good prediction, a very good skill for dry season. And so this probably it's the most appropriate objective function to do that. But we are also interested that our model has a good skill also for the rain season too. And then in order to do that, you need to modify your objective function. For example, using this objective function here. But in reality, we want to have a model that have a good skill for dry season and rainy season. And so you need to take in consideration the both objectives. And so our problem is effectively a multi-objective problem for parameter identification. Okay, and so in order to identify the Pareto set, considering, for example, 2 functions here, gx and hx, and the concept of the non-dominate solutions, it's going to happen, for example, for this 2 functions here, this is the green curve represents the Pareto set. And this is that we are interested. In order to identify the Pareto set, you are going to use NSGA2, this elitist non-dominated sorted genetic algorithm version 2. And so we have one initial population. Initial population is a candidate solution for this parameter. This coming from the literature, for example. And then this population is separated in different clusters. These clusters means Pareto fronts for at this iteration here. And front 1 is fully non-dominated. And front J here is a front dominated by front J minus 1, but dominates all of other fronts with lower order. But also this procedure here is going to use in crowding distance, because this is a kind of procedure to maintain the candidate solutions with spread in order to avoid a collapse that all population is going to in a very narrow region in the search space. Okay, and the off-print generation by crossover and mutation, like this is standard operators for genetic algorithm, and new sorting looking at a new non-dominant fronts. And so the process, so you generate a new population, and so you need to classify your in a different clusters, mean different fronts, and you are going to do that up to the convergence. Okay, and so let me to show you some numerical results. And first of all, we are going to identify the fast and the slow process. And we're going to identify the parameters associated to the faster processes. And so in order to do that, you can also use this Morris method. And the Morris method can show us 5 clusters of parameters. The cluster 1 is radiative flow, surface radiation. This includes 3 and 3 parameters. Turbulence, turbulent flow is 16 parameters, and carbon allocation, 6 parameters. Okay, and so I'm going to identify, firstly, this parameter here, the faster. And so after that, I have identified this parameter using my genetic algorithm for a multi-objective function. I'm going to freeze this parameter and start to identify the other group of parameters and so on. Okay? And there we go. Well, this is a we call it inverse crime because we start from these parameters here and we try to identify all the parameters using some synthetic observations. Okay, this is coming from the literature, and this is estimated, but also we did this calibration using data collected from Amazon region. And so this data is to represent the Amazon forest. Okay. And this, using this hierarchical calibration, I mean, different groups. And so we start from group 1 and then group 2 and so on. Well, the idea, for example, this is one thing that you can measure, this photosynthetically active radiation. It's PAR. And this is observed in a red curve, and the green is computed from our model. And this is a radiation balance. Other Other function is wind friction velocity and leaf area index. But as I said, the parameter estimation, it's going to change if you change your time scale for forecasting. In particular, for example, I'm going to show you some results when you're dealing with month range, day range, and hour range. The question is, for different time scale prediction, are the more sensitive parameter the same or not? Actually change. For example, the most important parameter here for monthly is this parameter here, and then this one, and this one, and this one, and this is classified in terms of relevance of the sensitivity impact for the model. And so you don't need to memorize all of this parameter and these numerical values. Forget about it. And so try to remember these three parameters here. And so this is for monthly prediction and daily prediction. You see that the parameters change a lot. And also, when you are going to, in the nowcasting, when you prepare your model for forecasting prediction, and then the parameter is going to change again. Not only the relevance of the parameter, but the numerical value for this parameter is going to change too. Okay, and so my final remarks is the calibration for process formulated as a multi-objective approach, and I use this version of genetic algorithm to compute the Pareto set, and the hierarchical strategy based on time scale of process in the ecosystem model was effective, and the Morris methods were effective to select 5 groups with different levels of impact sensitivity in the IBIS model. And this is just I put all together in terms of the groups of relevance for monthly, daily, and hourly, and different parameters. And the future works includes coupling IBIS model with the global model from the CPTAC. CPTAC is the Center for Weather Prediction and Climate Studies from National Institute for Space Research here in Brazil. And this center is responsible to produce the numerical weather prediction for the nation, Brazil. And the idea is to use this calibration for medium range, and also calibration for seasonal climate prediction, and try to see if we have a better prediction using this scheme of calibration. And coupling this IBIS with model BRAMS. BRAMS is regional or limited area model over the South America with a finer resolution than the global model, and also to apply this to other systems. One example is one special issue in inverse problems in engineering. This is 4 years ago. It's published this issue. It's about inverse problems in geoscience applications. One of this is calibrating a hydrological model by evolutionary strategy for multi-objective optimization. And also, we are going to apply in this SUPIM model. SUPIM model is the dynamics of ionosphere. And this is when you have some sun activity, and then this activity is propagated from the heliosphere to the heliosphere, impact on magnetosphere that there is some consequence like impact of in ionosphere dynamics. And so, for example, in terms of space weather, you know about aurora borealis and this spectacular views. And but in particular, Brazil, we have this is a geomagnetic South Atlantic anomaly. This is a picture from Wikipedia. Actually, this is some years ago, but now this anomaly it's over South America, most of part in Brazil, over Brazil. And well, we try to have some forecasting for using SUPIM model for 24 hours ahead in order to, this is visualizing the total electronic content of the atmosphere. And well, we published our results in this journal. And you can see here, this is our prediction, and this is observations. And for the March in 2011, June, and finally December. When we are different seasons, we have different concentrations of electronic content. And for example, this is one animation. When you have a quiet ionosphere, it's a standard regular solar activity. But when you have some ionospheric storm, this is you can see that over the poles there is much more electronic concentration, and maybe this is another way to see aurora borealis. Thank you very much for your attention.